Hello, everyone. I'm happy to introduce the first Computational Sustainability Open Graduate Seminar of this semester. And it is organized by 8 people in total. It's organized by Priya Donti at CMU, Genevieve Flashballer at MIT, Neil Gaikwad, also at MIT, Amrita Gupta at Georgia Tech, Neil Jean at Stanford, Brian Wilder at UC, and Kevin Winner at UMass. Again, the purpose of the seminar is for students in our network to disseminate research ideas that can be in progress or can be finished or published, or to present certain techniques that they found helpful for their work. And we're actively recruiting speakers for the semester. We have, I think, 3 lined up. But if you want to talk, after a month or so, then please let us know, and we'll put you on schedule. And for example, next week, in 2 weeks, we're going to have Priya Donti talk, and she will talk about inverse optimal power flow, assessing the vulnerability of power grid data. So you have something to look forward to. But this week, I'm excited to introduce Chen here at Cornell. He's a PhD student with Carla Gomes, and he's going to talk about end-to-end learning for the deep multivariate probit model, which is also published at ICML. So let's give it up for D.
Hello, everyone. I think I share my. Okay, it's working.
Do you need to share?
Yes, it's shared.
Shared? Yeah. Okay. Hello, everyone. I'm Chen. Today, I'm going to present my work called End-to-End Learning for Deep Multivariate Probit Model. It's about modeling multi-entities. So understanding the interaction of multiple entities is a central question in many real-world applications. For example, in computational sustainability, it's important to understand the spatial distribution of multiple species and how species are interacted with each other. And in computer vision, the detection of multiple objects are also correlated with each other. Because, for example, here, you can see in the picture, the occurrence of bicycle actually strongly implies the occurrence of wheels because they are it's just part of the bicycle. And also in natural language processing, a text always have several labels corresponding to its topic, emotion, and semantic meaning. Like here is an example for multi-aspect sentiment analysis. The sentence in color reflects different sentiments corresponding, but they share the same context, so it's very likely they are high correlated. So among a lot of different algorithms for modeling multi-entities, the multivariate probit model is a classic one for studying the correlated binary response. So how does this multivariate probit model work? The multivariate probit model learns the correlated distribution among binary response by using a group of latent random variables that are subject to normal distribution. It's here like Ri, where it captures the correlation of the binary labels Yi by modeling the correlation among this latent random variable Ri. So in this case, we model the correlation among binary labels by model the covariance matrix sigma here. Because the multivariate normal distribution is actually a probability distribution over a real number field, so we need to map it to the distribution over the binary vectors. By doing this, to do this, we use a threshold at 0 to map this to distribution. So formally, the conditional probability Yij equal to 1 condition the given feature xi is equal to the probability the random variable, the JS and random variable is larger than 0, and for the probability Yij equal to 0, condition xi is equal to the probability that the JS random variable Rij is small or equal to 0. Using this definition, we can derive the marginal likelihood of this multivariate probit model like this. Basically, you can say the marginal likelihood for each label is only related to the mean and the variance of the jth random variable Rij here, and also for the label 0. But for the joint, but in order to learn the correlation among multiple entities, we are more interested in the joint likelihood of this model. So that is the probability yi condition xi. Here, the index I reflects the index of different data because the distribution changes over data. You can say by using the definition shown before, we derive the joint likelihood as the integration over a high-dimensional space. Using some, here the constraint space is actually a hypercube AI, where when the jth label equal to 0, then the upper bound and lower bound on that dimension is infinite, is minus infinite to 0, and if the yj equal to 1, it's 0 to infinite. It's a little bit messy, so we can use actually we can use the linear transformation to somehow sort out this joint likelihood to be a cumulative density function of a multivariate normal distribution that is shown here is phi 0, where with specific mean and covariance matrix sigma. How do I do this? Basically, because the probability the jth random variable larger or equal to 0 is actually equal to the probability minus random variable Rij small or equal to 0. So we just times that random variable by -1 to get a different distribution. And this kind of transformation is linear, so we can directly apply the linear transformation of multivariate normal distribution to get this somehow more elegant result for this joint distribution. To be more intuitive, here I provide an example for 2 labels. Assume we want to model the distribution of these 2 species, these 2 birds, blue jay and American robin. We can model the probability the American robin is detected by the probability Ri larger than 0. Oh, here I ignored all the index I just for simplicity, yeah. And for the probability of the detection of blue jay is equal to the probability R2 larger than 0. So on the right side, it's actually the figure of the probability mass over this two-dimensional distribution. You can see the probability mass dropped in the first quadrant actually represents the probability that both birds are detected, and the probability mass dropped in the second quadrant represents the probability that blue jay is detected while the American robin is missing. Here we'll. What's the question?
Say again?
Say again.
So can you remind us what's R1 and R2?
Oh, R1, R2 here is the underlying random variables subject to a multivariate normal distribution. So in this case, R1 and R2 is a random variable subject to a two-dimensional normal distribution with specific mean and sigma. The mean, mu, and sigma is learned from model. So the distribution of R1 and R2 is actually a probability distribution over a real number field. So, but what we want to model is the distribution over binary vectors. So we use this threshold over at 0 to map this to distribution. Does that answer your question?
Yeah.
And this mu and sigma is specifically for these 2 birds.
Yes, the mu and the sigma are shared over all data points, but the mu depends on the feature xi.
Just a side note, I encourage everyone
to
everyone ask
can
questions.
interrupt me at any time and ask questions. So In order to model the correlation among these two species, we can change the covariance matrix. Like here, if we add a positive correlation, the probability mass changed from a right circle into some screw circle, yeah, ellipse, yeah, actually. And you can see after doing that, the probability mass drop in the first quadrant becomes larger, which means these two birds are more likely to be detected together, while the probability mass drop in the second quadrant becomes smaller, which is unlikely to say only one bird instead of another one. However, you can see the marginal distribution for those two species doesn't change no matter which kind of correlation they have. This is actually one of the advantages of this kind of model, because modeling the correlation among species doesn't affect the prediction performance for each of them individually. Here is a visualization of 100 species of 100 birds learned from our model using the eBird dataset. Here we color different birds in according to their habitat preference. You can see this picture reflects some interesting pattern. Like though mallard and Canada goose are more likely to be seen near humans, near some place near humans, like in the park, but they still have very strong correlation with other water birds. This is just an example of the covariance matrix we learned. Though the multivariate probit model gives a okay.
So
the
previous picture seems to be the embedding of the t-SNE, right?
Yes, we use t-SNE.
What's the raw feature we use to do this t-SNE?
Okay, so after training, we got a covariance matrix over all the random variables. So you can actually factorize the covariance matrix into two parts, like C times transpose C, and you use each column, each row of that factorized matrix as the feature vector for each species. You can say the actually each cell of the covariance matrix is an inner product for the ith row and the jth row. Basically, the inner product of two species, inner product between row I and row j represents the value of the covariance matrix.
So it's a kernel feature.
Yeah, you can regard it as the kernel feature.
And the dimensionality is the same. So the factors are of the same dimensionality of.
Yeah, it's called. You can use all kinds of different factorization because they don't change the inner product, change the value of the inner product.
Oh, yeah.
Very
and
good.
that reflects the interaction between those species condition on the feature. So, though the multivariate probit model provides a nice formalization for to model this correlated binary response, but the learning of this model is still very challenging because let's recall the joint likelihood. The joint likelihood itself is actually a high-dimensional integration over a constraint space AI. It doesn't have any analytical expression, so we can only estimate using sampling method. One straightforward way to estimate that form is to use rejection sampling. So we just draw samples from the underlying distribution and check whether this point dropped into the hypercube. And we count the number of times, like how many times it drops into the hypercube to estimate this joint likelihood.
It's the old technique to integrate, to do integration.
Yes. So actually this Monte Carlo sampling is actually the only way for us to estimate this kind of high dimensional integration, but people can do this in different ways. The most straightforward way, rejection sampling, doesn't work well because actually the probability the random sample dropped into the hypercube is exactly equal to the probability of this joint likelihood, which can be exponentially small. That means you need to draw exponential many samples to just get one sample dropped in that hypercube. So in most cases, you just get 0, and you can't estimate this by just doing rejection sampling. Maybe you need to sample 1 billion times to get some useful information. Another classic method to learn multivariate probit model is called GHK algorithm. This algorithm factorizes the joint likelihood to the product of conditional probability. This one is quite tricky. It's like it first factorizes the covariance matrix using the Chomsky factorization. So here, the matrix C is the triangular matrix. So, and using the linear transformation of the random variable R here, we can rewrite R into the sum of a mu plus C times standard normal random variable Z. And by doing this, you can say the distribution of the ith random variable now only depends on the value of previous random variables. So you can do a sequential sampling from the first random variable to the last, and you can also compute the conditional probability using one-dimensional quadrature. This actually, okay.
And so important sampling is better than rejection sampling because
yes.
Now it tries to force the sampling of.
Yeah, in this time it forces sampling, all sampling drops into the hypercube instead of doing something provides no information.
Mm-hmm.
But this method requires a sequential sampling, like you have to sample from Z1, Z2, and to the ZL sequentially. So you cannot actually integrate them with a deep neural network as well as boosting it with GPUs, because deep neural network requires a parallelized computation, but here you can't do it. Now comes to our method. Currently, I don't have a special name for this sampling method. I just call it the oh yes, I'd better come up with one.
We always generalize, so we'll think about it later.
Yes. Okay. The key idea of our sampling method is decompose the original covariance matrix into two parts. One part is an independent part. The V is actually a diagonal matrix, and another part is called a ratio covariance. It's an arbitrary covariance matrix. So recall the original probability PYI x condition xi is actually can be formalized into the cumulative density function of a high-dimensional multivariate normal distribution. This is actually the probability that R is small or equal to mu, where R is sampled from Gaussian distribution with 0 mean and covariance matrix sigma. So by doing this factor decomposition, we can rewrite R into Z minus W, where Z is subject to the independent multivariate normal distribution, and W is subject to the residual multivariate normal distribution. By doing this, we can rewrite the original probability by to an expectation of the conditional probability Z is small or equal to W plus mu condition W, where W is sampled from the residual covariance, the residual distribution. You can say, because this Z is subject to an independent multivariate normal distribution, the joint distribution of this term inside the expectation can actually be factorized into the product of each dimension, like this. So this part can be estimated directly using some quadrature for the one-dimensional Gaussian distribution. Further,
why can we do that? Why can we decompose it to be an independent covariance matrix and two independent covariance matrix components? And especially one is like why can we do that?
Because for any covariance matrix sigma, actually you can decompose into two parts. one part is a diagonal matrix. You can decompose into a diagonal matrix plus a residual covariance matrix. For example, if the minimal eigenvalue of this original covariance matrix is lambda, you can factorize the independent, at least for independent independent diagonal matrix V with the eigenvalue all equal to lambda, and have some residual part. So if you have a high dimensional normal distribution where the covariance is just a diagonal matrix, then you can actually, that means they are independent. Each dimension is independent, so you can factorize the joint distribution into the product of the probability in each dimension.
Is it like first sampling the transform space with regard to the eigen factors, and then convert it back to the normal space with the residue?
No, like I factorized the original covariance into two parts. One part is called independent part, another part is called the residual part. So you don't actually need to sample the, so for rejection sampling, you actually sample from the original correlated Gaussian distribution and check whether it's dropped into the hypercube. But here instead, we sample from a residual distribution and check and directly compute the probability that Z small equal to W plus mu. It's like this somehow is related to a raw Black-Whale theorem. It's about some sufficient statistic, and it's provable that this estimation, the variance of this estimation is strictly smaller than the estimation of rejection sampling. So is there any other question? Feel free to ask. I know this part is not very clear because it has a lot of mathematics here. So so by doing this, we can actually estimate our joint likelihood by doing an expectation over the inner product of a lot of one-dimensional CDF. And furthermore, we can actually rescale the independent part, the matrix V, as well as the residual covariance sigma and our mean to make it more elegant. It's like we can actually sampling from some, we call it rescaled residual distribution and compute the, use a CDF or one-dimensional, apply the one-dimensional CDF function to each sample directly and product them together and average this mean. We can estimate the joint likelihood without bias. So here is a end-to-end learning pipeline for our deep multivariate probit model. Here we employed a feature network to extract the feature from the raw contextual data, and this can help us compute the mean mu, which will directly implies the marginal distribution for each label. And we also parameterize the covariance matrix by parameterize the square root of it, because by parameterize the square root of it, we can make sure the covariance matrix is positive definite. And every time we will generate a batch of random standard normal distribution random variable Z, and multiply the square root of our residual covariance matrix with Z and plus mu to generate samples from our residual distribution.
What's your feature network?
Yeah, can you say
feature network. Feature network depends on your data type. Like for images, you can use any kind of type of CNNs to extract feature for you. And for some low-dimensional feature, you can apply multi-layer perceptron to extract the feature. It only depends on your feature.
Mm-hmm. But maybe to make it a little more concrete, can you give the examples what you use for like the birds and what you use for the vision or for the
actually for
just at a high level, but I think it
yes, actually in our experiments we use we use both NRCD data and Google Earth satellite image data to train the model for the eBird. For the NRCD data, we use a 3-layer fully connected neural network to extract feature, and for the satellite image data, we use ResNet to extract feature for computing this mu. Here, someone may note there's a diagonal matrix DI corresponding to YI. This is used to sort out the messy joint likelihood into a elegant conditional density, a cumulative density function of multivariate Gaussian distribution. This is just a diagonal matrix where the diagonal is either 1 or -1. It's just some linear transformation for the random variables. And eventually we can estimate this by average all the batches of the product of this one-dimensional CDF of our samples. This whole framework can be done in parallel using all kinds of popular machine learning packages like TensorFlow, PyTorch. You can do it easily. You don't need to have some handcrafted CUDA code to implement this. People may be interested in the convergence behavior of our sampling process, so we did some theoretical analysis in terms of the convergence rate. Here, the mu and sigma is a rescaled one, so we can assume the independent part of A is actually an identity matrix. And by computing the probability that the estimated value is close to the close to the real value within related arrow sigma epsilon, we can derive the equation 11. This basically says the smaller the eigenvalues of the ratio covariance are, the fewer samples we need to estimate the joint likelihood. Actually, each step here is a series of relaxing of the original estimation to eventually have a closed form. To be honest, this upper bound is really upper bound. It's far away from the real number, but it shines light on
in practice.
Yeah, but it still provides a lot of information in terms of in terms of the relationship between the number of samples we need with the ratio covariance matrix. You can see, and very straightforward idea is just to restrict the eigenvalues of this ratio covariance matrix to so that we can use fewer samples to estimate. So we conduct the experiments in terms of the low rank setting. If we restrict the ratio covariance matrix to be a low rank matrix, then there are only few eigenvalues is positive, and most of the eigenvalues are just 0. Here is the result for the eBird dataset, where we are trying to model the correlated distribution of 100 different birds, and we restricted the rank of our ratio covariance matrix from full rank 100 to 0. The horizontal axis on the left side represents the predictive performance of our model in terms of the negative log likelihood, and the horizontal axis on the right side represents the number of samples we need to with high probability have a accurate estimator within 10%, I think. Yeah, it's 10%. And you can see the line with marks X is the numeric estimation of a convergence rate, corresponds to the equation 9. We can estimate them using some numeric computation, which is the tightest bound for this theorem. And the line with circle marks as a theoretical upper bound with a closed form. You can see there's a huge gap but their patterns are
So
similar.
you are saying there's a huge gap between the theoretical upper bound and what you see in practice.
Yes, and actually the lines with X marks
Yes.
represents the number of samples we need in practice.
Yeah.
What does your performance mean? Like the
Performance means we optimize the model using maximum likelihood. So we use the negative log likelihood value as the
So the lower the better.
the lower the better, basically.
And so
And you can see actually unless the rank of this residual covariance matrix is really low, like lower than 5, the performance doesn't change too much. But actually the number of the upper bound drops a lot. Here the number of samples we need is scaled is using a logarithmic scale. So actually it drops from 500,000 to dozen of thousand, I think.
I have a question.
Okay,
So
what's your
why
question?
first, why this figure is from right to left?
From right to left. It's not from right to left. Oh, you mean the performance?
0 to, I mean, basically the bound seems very.
I mean,
and
it's
also,
just,
what's the meaning of rank 0? And that seems.
rank 0 means it's just a zero matrix.
0.
It doesn't affect so actually at that time the distribution of each species only depends on the mu.
Okay.
This is just a residual covariance matrix. We still have an independent part, which is an identity matrix. So when the rank is 0, we only need to sample once to get the exact estimation.
meaning that you are not really the interactions.
Yes, means that you don't care about interactions.
Yeah.
It's very interesting. The upper bound is going on. Why was it?
And I think he did this the other way around, and it's
No.
a little.
What I was saying? The upper bound is going up. No,
I mean,
it's the performance goes worse. Actually, as I reduce the rank of this residual covariance matrix, the performance goes worse, but the number of samples we need goes smaller.
Yeah, but the point of this graph is that what's incredible is that look at the performance. The performance stayed the same for so long. Only when the rank becomes really small, then you see the performance deteriorate. So, and obviously, as you know, so that's in practice, you don't need to have a very high rank.
Yeah, in practice, you don't need to have a full rank residual covariance matrix. You can restrict to some low rank to balance the computational complexity with the predictive performance. So here is actually the visualization of the residual of our covariance matrix. You can see, unless the rank is pretty small, like smaller than 3, even 3 is pretty much similar to the covariance of the full rank. Actually, the rank of the residual covariance matrix reflects the resolution of their correlation. Like as we gradually reduce the resolution, it becomes more weak, and eventually there is no correlation.
Yeah, exactly. Actually, I thought that's a very good point. In fact, it is indeed you are trading off. If you can lower the resolution and you still have very good performance. So yeah, I remember this.
And actually, in most cases, in real applications, the pattern of their correlation can be captured pretty well using a low rank covariance matrix. That means a residual covariance matrix. That means actually the correlation among them has some pattern. It's actually very similar to the assumption in matrix completion, where they assume the low rank correlation among the in that matrix. So here is the experimental performance for our model. Here we compared our model with 3 different groups of baseline. The CIM means the model that ignores the correlation, and it uses the same feature extraction network to predict the distribution of each entity directly, you can say the performance is much worse than all other models, because all other models consider the correlation among entities.
No more the better.
Yeah, the smaller the better. And another model, DMSE, is the former state-of-the-art gradient-based multivariate probit model. It used the GHK algorithms we mentioned before with MCMC sampling to estimate the gradient. That one has a similar performance in terms of the negative log likelihood with our model, but it trains much slower. Actually, our model is more than 100 times faster than their model, and we can adapt some huge neural network to handle the problem with different contextual data. But in their model, they can only handle the low dimensional data because of the constraint of GHK algorithm.
You mean their model is your model too?
Yeah, yeah. Actually, this is my previous work. We also compared another model which used the variational autoencoder to actually estimate the joint likelihood using a variational lower bound. That one performs slightly worse than our model, especially with the high dimensional data, because using variational autoencoder, the variational autoencoder sometimes works bad because it only estimates using the evidence lower bound, and in the evidence lower bound there's one part called the KO diverger part. That part will sometimes goes to 0 at an early stage, then the model no longer captures the correlation anymore.
Which, by the way, that's also your model.
That's Yuxiang's model, actually.
Well, you are
part of the author.
It's like the author.
So, in conclusion, we proposed a deep generalization of the classic multivariate probit model, and we provide an end-to-end GPU-boosted learning scheme with a better sampling process to estimate the joint likelihood faster and better. And we also provide a theoretical and empirical analysis in terms of the convergence behavior, so people will feel more comfortable, feel more confident to use this model in practice. So thank you for listening. So here are some references for related works. Do you have any question? Or do you want to clarify some part in this model?
So I guess for me here, so the high level idea, as I understand it, would be that you can you kind of rely on the network to figure out, to diagonalize in a way, the covariance in the data.
No, actually the high level idea is like, because we want to estimate the joint likelihood, right? Mm-hmm. And the computation of the high dimensional CDF of multivariate normal distribution is pretty hard, mm-hmm. but it's easy to compute when it's independent. Mm-hmm. So we're trying to separate the independent part and with the correlated part. So we only need to sample from the residual distribution, and every time we compute the CDF, conditional CDF over condition on the sample from the residual distribution, and we compute the CDF of the independent part, condition on the residual part, and that will provide you information for every sample. Like actually, extreme case for our model is exactly the rejection sampling, where you don't have an independent part. Mm-hmm. So the independent part, or the eigenvalue of the independent part, is actually 0. So in that case, we sample from the original distribution, check whether the probability is smaller than 0. Is actually that part will like degrade into the indicator function as shown before, and that will have a huge variance. So actually, the performance of this model depends on the structure of the correlation. If your structure really can only be captured using a residual covariance matrix, and actually the covariance matrix is like weakly positive definite, which means you cannot actually really separate them into parts, then the performance will degrade into the rejection sampling in some sense. But in practice, it works pretty well.
Nice. Do we have some questions from outside of this room? I see there are so many participants.
I'm happy to make a comment.
Some pretty impressive in reduction of processing time.
Yes.
Over the traditional method.
Yeah, that's a key point. That's also one key point in our work. It's like we take the advantage of the hardware. Like we can use we parallelize the whole processing the sampling process so that we can use GPU to help us parameterize a lot of samples. So we basically reduce the training time as many times as the cores in GPU, I think. So if you have a very large GPU, maybe they can parallelize it. Then maybe we can parallel 1,000 samples together. You can faster 1,000 times than the classic one.
And in practice, the speedups are at 2 or 3 orders of magnitude.
Yes, it's actually 2 or 3 order than the original model.
And it's valuable.
Yes. And
do you plan on having the code available for this?
Actually, I released my code in my paper. Oh, I didn't mention there. I released my code in my paper, and you can directly download it if you have any question about the format of data. It's quite straightforward. It's only 200 lines of TensorFlow coding, and you can adapt it easily.
Nice.
Yeah, and this is on your webpage.
Yeah, on my webpage. No, not on my webpage. It's on Bitbucket.
Yeah. So, but you.
Yeah, it's still a webpage. Yes.
Yeah, but you should.
I don't have a personal webpage yet.
Actually, we should make that available too through the. But you should actually do that to make it available through your webpage, and we'll. I mean, we at CompSust Net will. Yeah.
Yes. Yeah, I should do that.
And you know, I actually, I'm going to make a few comments, and in fact, it's still fresh. We just had the review, and you know, often I talk about how this, you know, you've heard probably over and over that I say computational sustainability is a two-way street, and you know, obviously I believe we are injecting some computational thinking. But often we also gain a lot. And, you know, this is a good example where D, you know, started with a classical model, this multivariate probit model that is, you know, a smart model, but it does suffer from computational issues. It is, you know, training this multivariate model is very challenging. And the way it's done up till now is using either this rejection sampling or importance sampling that, you know, are in the end slow ways of training this. But, you know, D brought in, you know, a new perspective and injected some computational thinking and taking advantage of, you know, GPU parallel hardware. That's how he was able to, you know, speed up by up to 3 orders of magnitude. And I think this illustrates beautifully a bit of this two-way street, how starting with a model, you can actually, you know, take advantage of this model, but then, you know, make it much stronger from a computational power. So I think that is an amazing example. Another issue that I want to emphasize to you that actually I mentioned it in the review too, and Warren was saying, wow, is that true? Well, often I tell my students, you develop a model and I want to see 3 applications. Sure enough, his paper has 3 applications. It shows obviously the motivating application is eBirds, but then he showed that this can be also used for image in vision, and in natural language context. So he had exactly 3 applications. So I strongly recommend that everybody does the same. Develop a methodology, a model, and then, you know, make it general enough so that you are not just solving your little problem, but show that it's general and can be applicable to in different domains. And D, actually, this is a beautiful case illustrating that. So, very good.
Professor Gomes, at that, you know well my interest is, I'll throw it out as a challenge to all of you. Extend this to the acoustic domain.
Well, we are working on that. Actually, yeah, stay tuned.
I will.
Very good. I can actually talk to you offline about that.
I'd like to.
Yes, yes, yes.
Okay.
I have a question. For
Yes.
Okay.
Since you were kind of, you know, comparing your models against each other, I'm interested to elaborate on what Carla was saying. Like, what were the kind of changes in insight that happened in between each model? And so, like, for example, from your first model to your last one, what are the key, like, differences in the way you did it that allowed you to, for example?
Okay. So maybe I go back to the last page.
You have to share again.
Okay. Okay, I'll share it. So here there are several models. So for the first one, okay, we just ignore the independent one. And the DMSE is my first work. Actually, it just adapted it used the multivariate probit model to, that one learns the joint likelihood using a gradient-based method where we still need to compute both the likelihood itself and its gradient. And in that case, we use GHK algorithms to compute the joint likelihood, and we use the
clarify it's an important sampling.
Yeah, actually, yeah, we use the GHK algorithm, which is the important sampling to estimate the joint likelihood. And for the gradient, we use the MCMC to estimate it. And that one cannot be paralleled in GPU, cannot be parallelized in GPU. So at that time, I just hand coded the C++ code to run the whole experiments. But
no, can you clarify? You still use the network to extract the features?
Oh yes, at that time I also use a neural network to extract features for this model to compute the mean mu. And after that, we did several improvements. And the second one, the MEDL -CVAE is the one where we use the variational autoencoder to estimate the joint likelihood using the using a variational way where we, instead of maximizing the joint likelihood, we're maximizing the evidence lower bound. And that one adapts some techniques in the recent popular paper called variational autoencoder. And in that case, it works much faster than the previous one, but the performance degrades at some time due to the learning process, because we're actually learning a lower bound. We are not sure how close the lower bound it is to the real joint likelihood. And now for this model, we directly learn the joint likelihood, but the estimation process now changes into the into a different way. And in this way, we can parallelize all our samples. We can parallel all our samples and adapt this model directly into GPUs, and so that we don't need to hand coding a deep neural network. We can use the popular machine learning packages to code this easily. Actually, one advantage of this new sampling method compared to MCMC is like in MCMC, you need to burn a lot of intermediate samples to reach the stational distribution. And actually, we don't even know whether it's already reached that stationary point or not, we just sample maybe 1,000 times we burn every 1,000 times samples, just get merely one sample from this estimation. But in our model, every sample provides information for our estimation, so it's more efficient, not only because we parallelize it, but also the sampling itself are more efficient than MCMC.
Thanks.
Do I answer your question?
Yeah, for sure.
Thank you.
Okay, and I think then we're going to wrap up the talk today, and then hopefully see you in 2 weeks when Priya is going to give her talk. Yeah? Okay.